Thank you, Yvonne. I was in Hiroshima in September, and I saw a poster, and Junko was sitting in front of the poster, and I said, "An international center on chirality, that is the coolest thing in the world." And then she introduced me to Professor Inoue, and I said, "An international center?" No, not, but I just misspoke. I said International Center on Knots. That's what I said. That's the coolest thing in the world. Then she introduced me to Professor Inoue. I said the same thing. That is the coolest thing I've ever heard of. And so I think they thought, oh, if we invite this guy, he'll come back in December. and it worked. And I was given a charge by Yvonne to give 2 tutorials about chirality. Which is kind of a hard thing to do because I'm told that this is a general and eclectic audience. And so I'll try to be both simple, sometimes sophisticated, but at the very least grounded in some history that hopefully will be new to some. Let's see. So today I'm going to give the first tutorial. I don't know how to make it go forward. Oh, there we go. I figured it out.
Are you using a pointer?
Okay. I have this one, and oh yeah, look at all this fancy stuff. Oh, I need that. Yeah. Okay. Okay. So today I'll talk about some just very general considerations, but I also want to talk a little bit about the chirality of knots at the end, since we're at a knot center. And then tomorrow I'll talk about especially crystallographic considerations of chirality, because my experience is in crystal growth and crystalline matter, but we'll also talk about braids, which are certainly related to knots. And then Friday, I will give a research talk on the chirooptical activity of knotted molecules. And we ought to begin such a tutorial with the definition. And the definition is this: a geometrical figure is chiral if it cannot be mapped to its mirror image by rotations or translations by themselves. These are called symmetry operations of the first kind. And chirality is the absence of symmetry operations that involve reflection, mirrors, or improper rotations that combine rotations and reflections. And we call these symmetry operations of the second kind. And that's it. I mean, that's sort of it, you know. Goodbye and good night. We're done. But of course, I have to add some content. Otherwise, I will be forever reviled as especially lazy. So let's add some content. And let's ask about how a mirror works. Now, anybody who shows up at a knot school is pretty smart. But I would conjecture that there are more than a few people sitting here who could not clearly explain how a mirror works, even though you may look at one every morning. And this is a print by the great Japanese printmaker Hokusai of a woman looking in a mirror, but of course everybody knows him for his iconic wave. And the great Spanish novelist once said, "How can things so trivial perplex an intelligence as mature as yours?" How does a mirror work? Let's start with a magic mirror. There is no such mirror that when President Trump looks into it, they see President Obama. Unfortunately, there is no such mirror. So it's a magic mirror. But even a regular mirror is pretty magical. So even when President Obama looks at himself in the mirror, something quite magical happens. Because it appears to exchange his left and his right. So you can see that President Obama is fixing his tie and his left hand is raised above his right hand. But in his mirror image, his right hand is raised above his left hand. And so a mirror seems to exchange left and right. But why doesn't it exchange up and down at the same time? Why left and right, but not up and down? It's a plain mirror after all. It's not some hyperbolic planar mirror, although I bet there are some people here who might be able to say something about that. In any case, what's so special about East and West compared with North and South? And the answer is that a mirror does not exchange left and right, and it does not exchange North and South. Rather, it exchanges front with back. But we think it exchanges left and right. And that's a psychological trick that our minds play on us. We imagine that if Mr. Obama were to walk behind the mirror to become his image, he would have to switch up what his hands were doing in order to become his mirror image. But Mr. Obama never walks behind the mirror to become his image. What really happens is something more akin to this weird picture from the internet. What really happens is Mr. Obama's front is exchanged with his back. But because in real life, we have no experience of American presidents whose faces are literally pushed through their heads and emerge out the other side, since that never happens to American presidents or it never happens to anyone, we think that the mirror is exchanging left and right when it's really exchanging back and front. And this is very confusing, and lots of people get confused by it. This is the famous illustrator, John Tenniel, who illustrated the book Through the Looking Glass by the mathematician Lewis Carroll. And this is Alice going through the looking glass through the mirror. And you can see that she's got her right hand up going in. And when she comes out, her right hand is still going up. And that wasn't the intent of the author. Lewis Carroll in 1871 asked an extremely sophisticated question through Alice in this book. He said, perhaps looking glass milk isn't good to drink. That is, Lewis Carroll presumed that Alice was being reflected down to her very molecularity. And that was a pretty sophisticated question in 1871, given what we knew about the arrangements of atoms in space at that time, not very much at all. So rotation is easy, but reflection is hard. So in 1957, the physicist Wu showed that the universe was chiral, left-right, asymmetric, at the level of weak nuclear interactions. This was the violation of the law of parity. And when the scientific world learned of this, they were absolutely shocked. Wolfgang Pauli said, in such a possibility, I would never have believed before January of this year. In other words, that there was something intrinsically different about left and right in the world of matter. And here he is with Wu. And here's the article that announced the violation of the law of parity in the New York Times. And then somebody told Paul Dirac about this experiment. And Paul Dirac was, I mean, Wolfgang Pauli was a pretty smart guy, but Paul Dirac was also a very smart guy. And he said, so what? And what everybody says, what do you mean, so what? This is a momentous discovery at the level of nuclear interactions. Left is different from right in some fundamental and intrinsic way. What do you mean, so what? And he says, look, I can rotate the universe by an infinitesimal amount, and you'd never be the wiser. But I can't reflect the universe in an infinitesimal amount. That's a big change. That's a huge transformation, reflection. And so he brought the whole thing down to the level of continuous functions in first-year differential calculus. And that was just, I think, a genius insight. The fact that he wasn't surprised by what surprised everybody else. Rotation is easy, reflection is hard. Some people use rotation to cheat. Here's the French sculpture, Auguste Rodin, and this is his Hands of God. What do you notice about the hands of God? They're both right hands. Well, what is he saying? Well, he may be saying God is special. Well, God is special by definition, so that's not a very interesting thing to say. He may be making a comment on the fact that God's creation appears to be dissymmetric, so God has two right hands, or he maybe is just lazy. It's much easier to cast one right hand twice and just rotate it with respect to the other one. Rotation is easy, reflection is hard. And Rodin cheated like this all the time. This is his masterpiece, The Gates of Hell. There are 7 castings of it in the world. The one I saw is in Ueno Park in Tokyo. And you can see the 3 figures on the top. It's the same figure, cast 3 times, just rotated, right? A lot easier to make one cast, repeat it, and rotate. Reflection requires a whole new sculpture. It's a big deal. Now, in fairness to Rodin, anybody who casts anything out of bronze 6 meters tall is by definition not really a lazy person. This is definitely hard work. So I call Rodin lazy, but I want to just qualify that he did some hard jobs. Rotation is easy, reflection is hard. Some of the greatest philosophers have really pondered long and hard about the difference between left and right. Immanuel Kant he said, look, my left hand and my right hand, they're the same, but not. The same and not the same. What's the nature of this difference? My right hand could not be any more similar to my left hand, except for the fact that it's not. And he called these things incongruent counterparts, which sounds better in German. Incongruente Gegenstücke, the same and not the same. Couldn't really figure it out. And philosophers that are called kids also have a hard time figuring it out. Ask a kid to tie their right shoe, and they will get it right about half the time. Why? Well, left and right is just a convention. It's a convention that's assigned to a real difference, but it's just a convention, and it has to be learned. Kids don't know anything about the non-conservation of parity, and that's why it takes them so long to learn which shoe to tie when asked. So here's a problem for you. Can you communicate to an intelligent being on some remote planet by means of a digital signal our understanding of the difference between left and right without referring to any common object in the universe? And if you want, you can presume that these creatures are bilaterally symmetric and have a front and a back, and you can presume that they speak in your favorite language. Can you communicate our understanding of the difference between left and right? The question.
So they speak your favorite language, but without an understanding already of that.
without an understanding, yes, without an understanding of left and right. They understand up and down. They live on a planet that you can explain, you can explain that gravity is an inverse square force law, and that that's why there's a down and an up, and you can, their eyes are in the front, so you can say we call the front the place where your eyes are looking, and but now you got to explain the difference between left and right. Is there a way to do it?
What's what mean by common object?
So what you can't do is you can't say, look up in the heavens and look for some constellation of stars that resembles a bear drinking a latte. And the bear is drinking the latte with its left paw. Yeah, left paw. You can't do anything like that. That would be a common object in the universe. Is there some other way you could do it? Could you use the laws of electromagnetism, maybe?
Tell them to do experiments with the parity violation.
Well, you're rushing ahead, but yes, that's what you would actually have to do. You would have to get down to the level of the weak nuclear interaction if you wanted to make this difference understood. Some people, when presented with this question in a class, often say, well, can't you use the right-hand rule or something from classical electromagnetism to explain the difference between left and right? And here we get tripped up always by the fact that magnetic fields are axial vectors or pseudo vectors. They're not polar vectors. And so assigning north and south to a magnetic field is just as arbitrary as assigning left and right to some creature. And so you actually have to get down to, and many people have been confused by the by pseudovectors and their influences on physical systems. Louis Pasteur, for example, thought that he could turn a symmetrical or holohedral crystal into a chiral or hemihedral crystal by growing it in a magnetic field. But he also didn't appreciate at the time that magnetic fields were pseudovectors or axial vectors. They were mirror symmetric. And we're going to rag on Pasteur quite a lot in these first two tutorial lectures. And not because I have anything against Pasteur. It's just that he can take it. His reputation is secure, and from the distance of the 21st century, I cause him no harm. But we're going to talk a lot of we're going to talk often about the things that Pasteur didn't quite understand. But it's okay not to understand things 170 years ago that we understand today. So this is the experiment that Wu did. She took cobalt-60, which is a radioactive isotope of cobalt that has spin 1/2, and she cooled it to near absolute zero in a strong magnetic field, so all the angular momenta were aligned. And so she created a situation that was perfectly mirror symmetric. And then she had two detectors, and she counted the number of beta particles that were spit out to the right side and were spit out to the left side. And she saw that more beta particles were emitted toward the south pole of her magnet. And this was the historic experiment that showed that parity is not conserved and that the universe is chiral. It's a perfectly mirror symmetric experiment with a very dissymmetric outcome. Incidentally, the theorists who predicted this effect, Li and Yang, won the Nobel Prize for this, but the peerless experimentalists who showed that this was so in a very challenging experiment did not share the Nobel Prize, even though there was plenty of room for a third laureate. And the reason for this is just that the 1950s was a very unforgiving time for women in science. Nevertheless, we can use her experiment to settle our conundrum about distinguishing left and right to our friend on planet X. So we can certainly explain that matter is made up of atoms, We can explain how the periodic table of elements works. We can explain where you can dig up cobalt ores and how to separate the isotopes from one another. And we can explain temperature scales and how to generate big magnetic fields. We can explain all of that without having to know the difference between left and right. It might be a long conversation, but we can have it. And once we settle all that, then we can give these instructions. Cool the atoms of cobalt 60 to near absolute zero, line up their nuclear axes with a powerful magnetic field, count the electrons that are flung out the two ends. The end that gets the most electrons, we call that south. We can use this label for aligning the protomagnetic field, the magnetic field in which the experiment was carried out. And this magnet then can be used to label the poles of any other magnet. So we can then say, go get some iron oxide, fashion it into a needle, and then label the ends of this magnetic lodestone. And then we can say, put a needle above a wire carrying a current away from you. We can explain how to make a battery and a wire, and we can say that the current is the direction that the electrons aren't going, and we can say put the needle that you've just labeled above the wire whose current is going away from you, and then we can say that the north pole of that needle will point in the direction that we call right, and that will do it. We have communicated this difference to an intelligent being on planet X. Now, this story ultimately comes from Richard Feynman, great physicist Richard Feynman. And it turns out, though, that the law of parity would be restored under charge conjugation. Charge conjugation means changing the charges on all of the particles, in essence, turning matter into antimatter. So the violation of the law of parity in matter is reversed in antimatter. That's called CP symmetry. And CP symmetry can be violated in some other kinds of special circumstances. But in any case, Feynman says, you know, you've been chatting with your pal on Planet X for some time now, and you're becoming friends. In fact, you may even be developing some romantic feelings, and you decide that you want to meet in the middle of the universe and get to know one another better. And so you agree to a certain spot in the middle of the universe. You take your spaceship there, they take their spaceship there, you hop out, they hop out. And if the alien should extend their left hand, Feynman says, run away, because that means what? The alien had to be made of antimatter, and that should you shake hands, you would, spontaneously combust. But we don't know where all that antimatter is, but Feynman gives this caution. So in any case, some people think that the violations of the law of parity, the difference between left and right, has lots of consequences. So here's a chart that gives the origin of biomolecular handedness. And this is sort of a speculative causal chain. Nobody really knows what happened. But you could imagine that you start out with cobalt 60 isotopes that are violating parity, that they emit electrons along with gamma rays that are circularly polarized. Those gamma rays that are circularly polarized could act on small molecules in the prebiotic universe, which could then make asymmetric sugars and amino acids and DNA and proteins and so on. And then through growth and differentiation, we end up with mollusks or cacti that spiral in one direction or another direction. And then ultimately, this leads to some kind of social organization where we have left and right. All roads lead somehow back to Mr. Trump. I don't believe, and there are schemes for extending violations of the law of parity to atoms and to molecules. I don't have time to discuss what these mechanisms are. Suffice it to say, I don't believe in any of this, because the energy differences that are associated with the violation of parity are tiny. 10 to the minus 14 kilojoules per mole for a pair of enantiomers of a common, enantiomers are mirror image molecules for a pair of mirror image molecules of a common amino acid. Tiny, tiny energy differences. And one would be really hard pressed to expect to see a chemical manifestation of energy differences that are so small. And I much prefer to believe in processes that I've actually seen in my own laboratory. For example, there are lots of autocatalytic processes in chemistry that break symmetry very simply, conveniently, and completely. This is a famous organic chemist, Kenzo Swai, who invented the eponymous reaction, the Swai reaction, where you take an achiral molecule and you do something to it and you get a chiral product. But this is an autocatalytic reaction where the chiral product serves as a catalyst for making more of itself. And so once you enter a scheme like this, depending upon what is the first molecule you make, that's going to catalyze the formation of more of it. And then you get more catalyst and on you go, and you're on a runaway train. And you can take this reaction and you can more or less just breathe on it. And the dissymmetric molecules in your breath are sufficient to bias this reaction to get it started in one direction. I'm much now, you know, processes like this are often stochastic. You run this reaction one time, you get 100% of one mirror image. You run it a second time, you get 100% of another mirror image. And it's much, but I think it's much more likely that our dissymmetry is a consequence of stochastic processes. We just happen to be the way we are because of the coin flip, rather than because of some intrinsic deep connection to dissymmetry at the level of nuclei. Although a lot of people kind of believe in this, a lot of people believe in this speculative causal chain because this is somehow deterministic. Like, you know, God decided where the beta particles were going to come out, and so that decided everything consequently. I much prefer to think that it's a manifestation of random stuff. Now, you may be good at recognizing chiral things. You may be good at recognizing chiral things from achiral things or not, but I'll show you a good place where you can practice. Let's see. Okay, I have to share something different. I hope this is okay for, I hope it's okay for the Zoom folks. Let us know if it's not okay for you, but if it's not okay for you, it'll be over soon. It's not it's not okay for the in-person folks. It's not okay for anyone. Here we go. Here should be okay for the no, it's not okay for me. You can't please everyone all the time. Okay. What's nice about this website is you can pick, it's just sort of any molecule you want. And it animates the symmetries that the molecule has. So this is hydrogen peroxide, H2O2. And all it has is rotational symmetry. And so that's the only thing that you can animate. But for example, if we want to go to some achiral molecule, we see that this molecule is superimposable upon its mirror image. And when I animate its reflection, nothing exciting happens because all the molecules are already lying in a common plane, so there's nothing to animate, and so it just kind of stays like that. But you can just go through, all the point groups you want and have lots of fun. This has two kinds of rotational symmetries. It has a threefold rotational symmetry and it has a twofold rotational. Oh, what did I do? No, it has, it's only C3. It has a twofold rotational symmetry, clockwise or anti-clockwise. But then we can go even down here to the dihedral groups. And you might ask, is this molecule chiral or is it not chiral? And you can animate all the possible symmetries that it has. It has a twofold rotation axis along X, a twofold rotation axis along Y, and it has a twofold rotation axis along Z. But in each of the orthogonal directions, it's twisted in some way. That's why it has the name twistane. And so this molecule is chiral because there's nothing I can do in the animation to make it otherwise. These molecules, water is a fun molecule. Water can be rotated, but it has two orthogonal reflections that exchange the hydrogens, or not. And so if you learn how to do this for molecules, you can learn how to do it for anything. And I don't know of a website that animates it as nicely for anything other than molecules. Now, I want to go back to where I was. Let's see. Is that okay? Am I back to where I was? Am I okay? Okay. Nobody sees me? Does the Zoom people don't see me? I have to change the share, I get. Oh, yes, I have to change the share. Okay. There we go. Okay, so why is symmetry or the absence of some symmetries important? And this is the consequence of the so-called Neumann-Curie principle, which is one of the most powerful ideas in all of physical science. That started out with a mineralogist, Franz Neumann, who said, it seems like the physical properties of crystals are connected with their shapes. So he was talking mostly about refractivity. But Pierre Curie then generalized this to any kind of physical system, not just crystals. And he said the physical properties of a system are invariant to its symmetries. And so there's a very strong connection between symmetry, in particular the absence of symmetry, and the physical properties that we can and cannot have. I don't know why this stopped working. Oh, that's because maybe that shouldn't be. No, I don't want to leave the meeting. That would be bad. I changed one thing too many. Let's see. Now I'm totally help. Well, I just wanted to work right. I'm
Oh, I see what you're saying.
let's just
is here.
Almost there. Put this back in.
And then presenter mode, I guess,
Presenter mode is
or presentation. Maybe that's
oh, this
one.
one.
It helps we can see the screen over here.
It's okay.
You can?
Yeah.
Okay, we're back. Yeah. So the physical properties, so the physical properties of effects, they're invariant to their cause. And so we can think about symmetry in the presence of external fields. There's a reason why we have feet and trees have roots, because we grow in polar fields, we grow in gravitational fields. For fish, gravity is not so important. So they don't need to manifest feet or roots. They just need an axis of locomotion, which need not be the axis of gravity. Radial area can have very ridiculously high symmetries, icosahedral or octahedral, because they don't have to go anywhere. They just float. Sometimes there are very left-right asymmetric organisms in land creatures, but that doesn't mean that they're made out of cobalt-60. It just means that other things can sometimes be important too, like genes and biology and all that kind of stuff. But Curie is most famous for the corollary to the symmetry principle, which translated is that phenomena are created by a reduction in symmetry. What's the most symmetrical thing you can think about? A sphere. Yeah, that's a dangerous question to ask topologists. So Curie meant that physical and chemical properties owe their very existence to the absence of certain symmetries. So here's a very symmetric thing. It's a sphere, and spheres are kind of dull. They have a radius, and that's about all the properties that they have. But you can drill a hole in a sphere, and suddenly it has a dipole moment. And you can drill another hole, and you can drill a third hole, and all of a sudden you have chirality, you have life, you can go bowling. All kinds of things happen, but only when you reduce the symmetry. High symmetry is death. Low symmetry is fun. Stuff begins to happen. Symmetry arguments are predictions that are based solely on the symmetry of some kind of model, some kind of physical model. And such arguments, these are called symmetry arguments. And the heart of a symmetry argument is the non-equivalence brought about by the absence of suitable symmetry operations. And so, we can say if something is optically active in solution, we know a lot about it. We know it cannot have any improper rotation reflection axes. We know it can only have proper rotation axes, and it must be chiral. If something has an electric dipole moment, we know it has to have one polar axis. It may be chiral, but it doesn't have to be. If something has an electric quadrupole moment, it may be chiral. It must be isotropic. Isotropic, that is having more than one high order rotational axis, threefold or fourfold. Symmetry arguments are very powerful because they tell you exactly what properties you can and cannot have, what cannot be measured in a laboratory. The limitations of symmetry arguments are that they are necessary but not sufficient for the realization of phenomena. In other words, they provide no information about magnitude or direction. They're just yes or no questions, but they don't tell you how much. So the absence of being able to measure something does not necessarily mean that your symmetry argument failed. It just may mean that you need to do a better experiment. People often ask, can chirality be put on a scale? Can it be quantified? And the answer is yes and no. Yes, it can be, but there are so many possible scales or chirality functions that you can invent that the answer is practically no, because none of these scales are privileged. There's no universal measure of chirality. There are a million different ways you can measure it, but there's no measurement that's any better than any other kind of measure. There's no scale that's better than any other kind of scale. And so it's a kind of a fool's mission to try to say that this thing is more chiral than that thing for a particular reason, because you can always come up with a particular reason why the other thing is more chiral than the first thing. So here's a riddle. What's the difference between President Obama and an ammonia molecule? An ammonia molecule doesn't need a mirror to invert itself. It's simple enough that it can just do it. So here's an ammonia molecule where we've labeled the 3 hydrogens with different isotopes of hydrogen. So this is hydrogen, deuterium, and tritium. And this is a chiral molecule. It is asymmetric. It has no symmetry, no rotational or reflection symmetry, but the hydrogen atoms can undergo a propeller-like inversion and pop out on the other side. And then we can turn the molecule over by 180 degrees, and we can see that this molecule is the non-superimposable mirror reflection of this molecule. That's the thing that Obama couldn't do by pushing his face through his head and making it come out the other side. So ammonia doesn't need a mirror to invert itself like President Obama. And this molecule goes through a flat achiral transition state. So clearly, the transition structure is not chiral. All the molecules are occupying a common plane. Are there molecules that can go from object to mirror image, but without ever going through an achiral transition structure? And in fact, there are such molecules. Now, if you've never taken a class in organic chemistry, it may be non-obvious that this is such a molecule that can be right-handed and left-handed. The structures can interconvert with one another, but they can never go through an achiral transition structure. That may be hard to see, so let me try to break this down for you. This molecule was synthesized by Kurt Mislow in 1955, and it's a molecule where there's some left-handed stuff on one end, and there's some right-handed stuff on the other end. And it looks like this molecule could be mirror symmetric. But it turns out that this central carbon-carbon bond here is kind of crowded. And so all of these nitro groups can't fit in a common plane. So the structure has to be twisted somewhat. And because the structure is twisted somewhat, it obviates the mirror plane that relates the chiral groups that are on the opposing ends of the molecule. And this molecule can convert into its mirror image by twisting around this central bond and then rotating the hands to get back to where they would be in reflecting positions if this molecule could accommodate a mirror plane. And so this is an example of an anti-mirrorization process where right-handed goes to left-handed, but it never goes through anything that's achiral. It cannot. An anti-mirror interconversion between molecules that can never become achiral.
So during the twisting process, it never reaches a planar state.
It never reaches a planar structure. It can twist like this. It can twist. It can go from like this to this in the middle, but it can never cross. It can never cross because it gets too crowded. So it can be like this or like this, and the symmetric groups on the end can compensate by rotations about their single bond. So you can get mirror image structures, but you can never go through a mirror. And so this is interesting because if this has some property that's associated with its chirality, for example, the way it scatters circularly polarized light, this molecule will have an equal and opposite effect. But in order to go from something that's positive from something that's negative, you have to go through zero. But that zero has to be a chiral zero. It has to be a chiral structure that by necessity has a measurement of zero for the property in question that relates the two mirror image molecules. So in chemistry, mechanism and geometry matters. In topology, everything's made of rubber. Mechanism and geometry don't matter. And so here's something likewise made of rubber, like laboratory gloves. And if you've ever had a glove on your left hand and you pulled it off, it suddenly becomes a right-handed glove. But it never goes through an achiral transition. It goes from left-handed to right-handed, but without ever going through an achiral state. Now, a topologist could force the issue and just say, well, I'm going to declare that this thing becomes absolutely flat at some point, even though in reality, it doesn't actually become flat like that, but we can just declare that it is so because we've hopped over from chemistry into topology. That brings us then to some really fundamental differences between chemistry and topology. And I'll just make a few comments about the chirality of knots to the extent that I'm able. So these are the two simplest knots I'm sure everybody's familiar with, the unknot and the trefoil knot. And the unknot is just a circle. It's obviously superimposable on its mirror image, but the trefoil knot is chiral, and it is not superimposable on its enantiomorph, on its mirror image knot. But how do we know that a knot is chiral if it can have innumerable presentations? I can say it's so, but it's not that interesting when someone tells you something that's so. You want to know why it's, you want to know the why of it. How can we really be sure that there's no way to interconvert this structure into this structure by continuous deformation? And the reason we can say this with surety is that we have people called mathematicians who write down theorems and prove them and tell us stuff. And so it has been proven that there is no continuous deformation that will convert the right-handed trefoil into the left-handed trefoil. Let K be, so here's the theorem, let K be a knot with a reduced alternating projection which has an odd number of crossings. Then K is topologically chiral. It cannot be deformed into its mirror image. This is a theorem for some kinds of knots. It's not a universal theorem for all knots. So if you have a knot like this and it's directed and it has a minimum number of crossings, and those crossings are all alternating over, under, 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 then that knot is topologically chiral, and there is a proof for a knot of that kind. There are lots of different proofs for different kinds of knots. To the best of my knowledge, there is no universal proof that covers all kinds of knots. So given an arbitrary knot, I don't think that there's one way of establishing unequivocally, but I could be wrong, that that knot is chiral, but for specific classes of knots, it can be shown. The next most simplest knot is amphichiral. Amphichiral means that it can be converted into its mirror image by continuous deformation. And here's an animation of the conversion of a right-handed figure-8 knot into a left-handed figure-8 knot. We presume the ends are simply connected. In this animation, what's being shown are, I don't know where the animation went. What's being shown are a series of Reitermeister moves, and I think everybody knows that Reitermeister moves are the kind of chess moves that topologists allow themselves. They allow you to change the presentation of one structure to another without changing anything fundamental, that is, without crossing or breaking any edges. And a series of Reitermeister moves will convert a right-handed figure-8 knot into a left-handed figure-8 knot by some sequence of moves. In this sequence of moves, this knot never becomes achiral, but it could. It could. There is a symmetric presentation for this knot. It's just not shown in this sequence of Reitermeister moves, but there is a symmetric presentation that has an improper fourfold axis, where if you rotate this thing by 90 degrees and reflect in a plane perpendicular, you get back to where you started from, and that's an achiral point group. How do we know if an amphichiral knot cannot have an achiral presentation like this old molecule from Mislow, and again, we have mathematicians for these kinds of things. There's a theorem, no prime knot, that is no composite knot, that is rigidly negatively achiral, orientation reversing through topological transformations. That's a theorem. No prime knot is rigidly negatively achiral. And the 817 knot is a demonstration, and there's a proof, and it's not a very long proof that comes out of this book that shows that, yes, there are knots that are amphichiral, like the Mislow molecule, that can interconvert from one enantiomer to another, but without ever going through an achiral transition state. That is, they must have a chiral zero somewhere. Now, the vast majority of knots, however, are neither achiral or amphichiral. The vast majority of knots are chiral, just like the vast majority of molecules are chiral. And if you go to the Wikipedia page, you can see that the number of chiral knots increases astronomically, as do the number of knots with the number of crossing points. If we look at amphichiral knots, they are far fewer. This is the figure 8 knot. This is the 817 knot, the one I just showed you. This has an achiral transition structure. This does not. One of these 5 does not have an achiral transition structure. For a long time, it was conjectured that amphichiral knots must have an even number of crossings, but it was recently shown by a guy called Hosta, that that's not true any longer. He found a knot with 15 crossings that is amphichiral, that is amphichiral. So knot theory is alive and growing all the time. These are the next 2 simplest amphichiral knots. How do we know this? Well, it's amazing what knot theorists can deduce from the polynomials and invariants that they assign to knots. And this is a beautiful subject, and I wish I could tell you about it from an authoritative perspective. I can't, but I am keen to meet real flesh and blood living knot theorists. And so if you happen to be one of those, definitely please shake my hand so I can at least say I have indeed met bona fide knot theorists made of flesh and blood. Now, these are chemical knots made out of 60 carbon atoms, and I'll talk some more about these particular 3 structures on Friday. And I just want to say that when you cross over from topology to chemistry, then you got to be a little bit careful. So I have this flashing light here because chemistry is not mathematics. Bonds in chemistry are electrons in a vacuum. They are not yes or no propositions. Graphs of molecules are drawn by people, and they are drawn by convention. And what is a bond and what is not a bond is a judgment call sometimes. Whereas in topology, you decide what is an edge and what is not an edge, and you decide that forever, and that is inviolable. So when you begin to mix chemistry and topology, you can find yourself on some in some tricky territory. Mathematicians sometimes have the privilege to say, QED, I'm done. Chemistry, at best, chemists can say, what about that molecule? There are so many molecules that there's always a counterpoint to whatever judgment you want to make. Now, I'm being self-deprecating about chemists, but I'll try to restore a reputation by pointing out what you probably already know, and that is that it was chemists, in any case, that created knot theory. It was Lord Kelvin's speculation that the different elements in the periodic table were just different knots tied in the luminiferous ether. That was his conjecture, and that led his colleague Peter Tate to the first enumeration of knots. So after Lord Kelvin, knot theory left chemistry for a long time. It has come back in recent generations, and we'll pick up the story in tomorrow's tutorial tomorrow.